Hello students, welcome back. We just completed section 1 of this notebook, which reviewed discrete random variables. Chapter 3 of our textbook, lessons 4 and 5 of our Canvas modules. Now let's go to section 2, continuous random variables. Let's begin with a reminder. What is a random variable? It's a real function that assigns a numerical value to each outcome of the sample space. In a special case, if this random variable takes a discrete set of values, or more precisely speaking, if the image set x of s is a discrete subset of R, in that case we say the random variable x is discrete. What are the examples of discrete subsets? Any finite subsets will do, or just like set of integers, infinite but discretely distributed sets will be also okay. But then again, what about the other case? What if, for example, this image set includes an interval? Say, for example, x of s is interval 0 to 1, or 0 to positive infinity, or negative infinity to positive infinity, those kind of things. In that case, the contribution of one number out of infinite to the many is 0. You see, if you have entire integers, for example, they're discrete, so you can have infinite series. So even for one number out of infinite to the many, it could have some positive non-trivial contribution. But for uncountable many numbers in entire interval, that's impossible. And therefore, this concept, the probability mass function, this expression becomes utterly useless. The probability that random variable taking the value precisely equal to x, that x is one real number out of entire interval 0 to 1 or 0 to infinity, that never happens. Actually, it does happen, but just probability is 0. Kind of complicated situation. So we want to avoid that. So where do we start? We start from Cdf, because that concept stays valid. We begin from the cumulative distribution function, which we continue to use capital F of x, and is defined as the probability that the random variable is taking real number x or less. So value of this random variable is x or less, so that real numbers go all the way back to negative infinity. So we are talking about another uncountably many real numbers there. So combine all those, then we can consider a positive non-trivial contribution from there. Now, in a special case where this cumulative distribution f of x, capital F of x, is a continuous function, we say the random variable is continuous. So continuous random variable means continuous CDF. Now, if you have continuous CDF, then we can consider something called probability density function, and typically we use lowercase, so that we have this relation. Does it ring a bell? It should. Everybody went through Calculus 1 as prereqs, so this should ring a bell. Apply the fundamental theorem of calculus. Then what's the relationship between the capital F and small f? Small f is a derivative, and capital F is an antiderivative. Of course, that's when capital F is differentiable and so on and so forth. But let's assume all those because this is just 3000 level, undergraduate level course. If you go higher up, things can go more complicated. But for now, let's just stick to simpler cases. Let's assume capital F is differentiable and small f is continuous and so on. So that we have this relation. And the small f is called the probability density function, PDF, and capital F is called cumulative distribution function, Cdf. As before, we're going to put together Cdf and Pdf and put together, and we're going to call continuous probability distribution. Kind of cheating, yes, but I don't see any better way to explain what continuous probability distribution is. All right, we went through Cdf and Pdf. Let's have some visualizations. Here are a couple of examples of Cdf and Pdf. Let's see, here are PDFs. I would like to have those in a single viewing window. Smaller font here. Okay, I have all those here. All right. So here are a couple of examples. Blue example here, we have PDF up here and CDF down here. Red example, PDF and CDF down here. Look at CDFs first. To the left, to the negative infinity, we go down to 0 because this is cumulative distribution function, so probabilities have to be added up. But down here, to the negative infinity, nothing was added up yet. So go to 0 and add it up, add, so going up, up, and then stops at 1 because now everything was added. Now for discrete probability distribution, each time we add something, a probability mass was added. So some chunk was added. So we have jump, jump, jump. And then step size was probability mass. But this time we have accumulation of infinitesimals. So we have a smooth curve. Did I say smooth? Excuse me, I should have said continuous curve. Continuously going up. Continuously going up, but not as steadily. That's because of these kind of wriggles, but still, from negative infinity to positive infinity, going up, up, up anyway. Also, please compare these with the fundamental theorem of calculus. So, area underneath the curve is same as a net change, this minus that. So, area underneath the curve, this blue region, is the net change of this blue portion of the graph. And the same goes to red. So net change here, capital F of B minus capital F of A, versus area, integral A to B f of x dx. So they're the same, and that's coming from the fundamental theorem of calculus, and they both represent the probability between A and B. Now I'm using less than or equal for both. Will those make difference? No, not really, because this time we are looking at continuous random variables here. So one real number out of uncountably many has no contribution. So whether I use inequality as semi-inequality or strict inequality make absolutely no difference there. And if you calculate probability of this x equal to something, anything, that probability is always 0. It's basically area of a line segment. Here are some further visual examples. I have to warn you, it doesn't always happen this way, but in 3000 level, we're going to keep simple. So we're going to stick to the examples that we can see these kind of behaviors. And we can consider continuous random variables, or the PDF, the probability density functions of continuous random variables as a limiting case of the probability histograms of probability mass functions of discrete random variables. Oh my goodness, it was too long. Even if you forgot what I said, including all those errors I made, just look at the picture and try to understand visually what's happening here. Let's go back. We begin with some probability histograms here of some PMF. Yes, we have non-overlapping rectangles of same width, probability histogram, and more and more and more. Look at the limit. What do you see? So histograms are converging to probability density functions. Do you see that? And probabilities are the area, so look at these areas. Remember, in histogram, in advanced histogram from way back in chapter 1, probability or relative frequency at the time corresponds to the area, not the height, right? The height corresponds to the relative frequency or probability when we have the same width. Well, all right, we have the same width, so it turns out okay, but still focus upon the area. Remember, if we have the same width, then area and height are proportional, so we get an illusion that we are looking at height, but it's actually the area that we are looking at. Now here's another visualization, this time CDF versus all gifts. So we have those step functions here. All right. And those are CDFs associated to PMF that we saw before. We have those jump, jump, jump. But then again, we add more and more and more rectangles. And likewise, we put more and more intervals. And what do we have? We have apparent convergence. So in many cases, continuous random variables or continuous random variables appear as the limiting cases of discrete random variables. Of course, it doesn't always happen like this. It's just that we're going to focus upon simpler cases like these in undergraduate level. In general, of course, things can be really rough, and the general definition has nothing more than this. Here is the definition of the CDF, and then if CDF is continuous, then we have continuous random variable. And in that case, we have things like this. Yeah, that is true. Even when capital F is not differentiable and not even continuous, if it is just piecewise continuous, still we have this kind of thing. And small f doesn't have to be continuous, and yeah, that's basically opening a hell gate. But that's too complicated, so we're gonna stick to simpler cases where we have this kind of nice relationship between capital F and small f, derivative antiderivative relations, and fundamental theorem of calculus. All right, we went through the concept, visual examples. Let's have a summary. Here are the summaries of CDF and PDF. First is easy to see, starting from 0, increase up, all the way up to 1, because this is basically accumulation. Nothing was added yet, so we begin from 0. Everything was added, then the probability is 1. That's easy to see, and we saw the picture. The proof, on the other hand, is not that simple. This part is okay. Nothing was added, so x is less than negative infinity. That's impossible, so probability of empty event, that's 0. X is less than positive infinity, that's everything. So probability of entire sample space, so that's 1. That's easy to see. Why are they increasing? That's not that easy. It turns out if you express those as events, then it'll turn out we have a subset relation because x2 is greater than x1. So we have inequality like this. If you can follow, great. Otherwise, let's just move on. The derivative relation. Okay, all right, we saw that before. Oh, density function is always positive. Okay, that's true because Cdf is always increasing in its derivative. And then, oh yeah, this is important. Area underneath the curve, entire curve, is always 1. This area underneath is always 1. This area underneath the curve is always 1. That's because that's probability of everything accumulated. So probability of everything, entire sample space, that's always 1. And therefore, we have to have those coming down to 0, either asymptotically or actually hitting 0. If it doesn't, goes back up or something, then the area is infinity, so everything breaks down. Yeah, negative infinity, positive infinity, go down to 0. Otherwise, integral will become infinity. Probability for any random variable taking precisely a real number x, that contribution is 0. So whether a random variable is strictly less than x or less than or equal to x, no difference. Use your common sense and you can easily see that. To prove it, oh my god, actually that's pretty hard. Here's a summary of proof, but I don't know whether you can follow it or not. It requires real analysis. And the probability that random variable taking a single real number value is 0, and that actually follows from the previous result. So it's not too difficult. And then the fundamental theorem of calculus. The proof is actually a bit tricky, but I'm not going to dwell on it too long. Anyway, here's a summary version. Some are immediate from visual examples. Look at these visual examples. Some are not that immediate. Okay, how much time do we have? Looks like we can discuss median versus quarters and percentiles. This real number x value x star, so that the Cdf value is certain p is called percentile, where p is say 0.5, then it's median, half the probability, 0.25 and first quartile, 0.75 and third quartile. If it's 0.85, then 85th percentile, 0.90, then 90th percentile, and so on. Do you have enough time for an example problem? Well, I'll give you a sketch of this problem. Here's a density function, and A is not determined. How do you find it? Well, the total probability is always 1, so this integral has to be 1. So A is times this integral is 1, so 1 over that integral. And if you calculate the integral, you can find out A value. Good luck calculating the integral. You can do it through integration by substitution. Oh, excuse me, this is through integration by parts. It's even worse. Now find out the probability that x is between 1 and 3, and that is just integral computation, 1 to 3. So previously I found A value is 4, and integral 1 to 3. X is between 1 to 3, so integral 1 to 3, and calculate that using integration by parts again, and do your computation. You're going to get this kind of value. I'll stop there. I'm not going to go too deeply into integral computation, especially integration by parts. I'll stick to substitutions most of the time because integration by part is covered by calculus 2, and not everybody completed calculus 2 here.